Alright, let's have a go at solving some systems of linear equations using Gaussian elimination. I'm going to assume you've had a look at the Khan Academy pages I've linked to in the notes. But if you haven't, let me summarise briefly. We're going to turn each of these systems of equations into an augmented matrix. Basically, we're going to put the various coefficients into the columns of a matrix. Then we're going to use that matrix, we're going to manipulate that matrix using particular row operations in order to solve this system of equations. The row operations we do are basically just using elimination, normal elimination methods, to solve the simultaneous equations. But we're going to save ourselves from having to write x's and y's all over the place. So if you're wondering what row operations are allowed, it's whatever you would be allowed to do with these equations when you're doing normal solving simultaneous equations by elimination. Let's begin. The first thing I want to do is turn this system of equations into a matrix. My matrix is going to have 2 rows and 3 columns. It's going to have these coefficients of x, 1 and 3, these coefficients of y, 2 and -1, and be augmented with these result values, 4 and 5. Keep in mind this is just a shorthand representation for this matrix. Sorry, for these equations. All I'm doing is putting x variable here, y variable here, result constant over here. And this is equation 1 and this is equation 2. I'm not normally going to write this, I just wanted to show you on the first one. So, what I'm going to do to solve this is manipulate this matrix until I have zeros to the bottom left of that diagonal. Everything below here has to be zeros. Then I'm going to go back up the matrix and replace everything above the diagonal with zeros as well. And if I have ones left on the diagonal, I can easily solve my equations. So, step 1, choose a pivot. From the leftmost column, that's not all 0, I'm going to choose something as my pivot. Now, in theory it doesn't matter, but this one's already 1, so that's really nice. I'm going to leave it as 1. Step 2, move it to the top row. I don't have to move it to the top row, it's already there. Step 3, eliminate everything below. Now this entry is 3. If I want to eliminate it, I have to make it into 0. I can do that by subtracting 3 lots of the first row. So in my new matrix, I'm going to go this row, row 2 is going to get row 2 minus 3 lots of row 1. So I'm going to get the first row doesn't change, and the second row is going to be subtract 3 lots of this. So 3 minus 3 of that is 0. That's what I wanted. -1 minus 3 lots of 2 is -1 minus 6, which is -7. And 5, whatever I do over here, I have to do over here. 5 minus 3 lots of 4 is 5 minus 12, which is -7. And I can stop there because now I've got only zeros below the diagonal. This is in row echelon form. What I really want is reduced row echelon form. I want to go backwards up the matrix, turning these diagonals into 1 and eliminating everything above. Again, remember, what I'm really doing is manipulating these equations using elimination. I've now got -7y is equal to -7. So I'm going to turn that into 1y equals 1. Then I'm going to substitute it in here to eliminate y from the first equation. So, how do I get there? I want to put 1 here. So, row 2, I'll write it backwards, row 2 becomes negative row 7, row 2 over 7. Got to think about what I'm doing here. Top row hasn't changed. Bottom row is going to divide by -7. 0, 1, 1. I now know y is equal to 1. So let's eliminate it from the row above. To get rid of it from the row above, I'm going to leave the bottom row alone. I have to put into row 1, I have to take away 2 lots of row 2. Row 1 minus 2 lots of row 2. So nothing happens here because there's 0 here. That's what makes that nice. Take away 2 lots of this. 2 minus 2 is 0. 4 minus 2 is 2. And I can straight away see, therefore, x equals 2 and y equals 1. One lot of x is 2 and one lot of y is 1. We should check this. If you want to, you can check by putting it into the original equations. X plus 2y is 2 plus 2 times 1, which is 4, correct. And the second equation says 3x minus y is 5. 3x minus y is 3 times 2, which is 6, minus 1, which is 5, which is correct. Now this looks like a lot of bother, doesn't it? To solve these equations using substitution will be pretty easy. But that's not the point. The point is to learn to use a matrix to do it, because this kind of algorithm can be programmed very easily in computers. This is why this was developed. It seems very easy for a 2 by 2 to go to use a different method. It seems harder to use this method. But once we have 3 by 3 or 4 by 4 matrices, it's much, much easier to use this method.